Hi, my name is Meir Yosef Levy, and I'll be presenting our paper, EPiC, Ensemble of Partial Point Clouds for Robust Classification, a collaborative research with Professor Guy Gilboa, Technion, Israel. Point cloud classification is crucial for autonomous driving and robotics. Our research aims to improve the resilience of point cloud classification networks when facing real-world corruptions. To accomplish this, we conducted our study on the ModelNet C dataset introduced by Ren et al. In 2022. This dataset extends the widely used ModelNet 40 dataset by incorporating 7 types of corruptions, including scale, rotation, jitter, as well as the addition and removal of local and global elements. These corruptions mimic real-world scenarios such as occlusions and acquisition systems inaccuracies. Our method is based on an ensemble learning and sampling, and we do not suggest any new architecture. Thus, it is applicable for any point cloud classification network. The ensemble consists of 3 subsampling strategies: random, involving the selection of k random points; a patch, consisting of the k nearest neighbor of an anchor point; and a curve, a random walk initiated from a given anchor point. Note that random represents global subsampling, while curve and patch are localized ones. In training phase, we train 3 separate networks, each dedicated to one of these sampling strategies. We are sampling subsets of the cloud and train the network on much harder tasks. Therefore, the overall accuracy is degraded, but this is compensated by the ensemble, leading to an improved accuracy over the vanilla network performance. In inference, we employ farthest point sampling to choose 4 anchor points. From each anchor point, we retrieve both a curve and a patch. This, along with the 4 random subsamples, form an ensemble comprising only 12 members. Each subsample is then predicted by the corresponding pre-trained network, and to obtain the final prediction, we aggregate the results using a simple averaging method across all sampling instances. Here, we present our results on several widely used networks. MCE stands for mean corruption error, where lower values are better, and OA represents overall accuracy on the uncorrupted dataset. Our approach improves the robustness of all examined networks and enhances the accuracy of most of them. We assess different types of architectures, including CNN-based, transformer-based, and graph neural networks, and our approach successfully enhances the robustness of all. To provide a comprehensive perspective, we have evaluated our method alongside state-of-the-art augmentations, which consist of a combination of point wolf and RS mix. As illustrated in this table, our approach continues to demonstrate its effectiveness even when augmentation techniques are applied. When employing RPC in conjunction with our approach, we achieve state-of-the-art results yielding an MCE score of 0.501. Why is our method so effective? Subsampling creates instances where the samples remain unaffected by the corruptions. For instance, consider the cone and guitar example, where the patch subsample remains unaware of the existence of local corruptions. Another example is the chair in the top left corner, where the random walk may not be affected by the outliers. When we initiate the process from an anchor point within the sample, it is highly likely that the k nearest neighbors will primarily consist of sample points rather than outliers. However, what happens when some of our ensemble members are exposed to the corruption? For this, we conducted an experiment and split all tables instances in ModelNet C into exposed and unexposed group. Then, we averaged the predictions of each group. The unexposed instances predict the sample in a certain and correct manner, while the exposed instances are misclassifying. However, since the uncorrected classifications roughly can be modeled as noise, it is diminished by a simple mean. Therefore, the overall prediction is mostly affected by the unexposed samples. To compare our ensemble with others, we measure diversity by analyzing the normalized correlation matrix. As lower the correlation, the diversity is larger. This matrix shows correlation within an ensemble of 3 different architectures: point cloud transformer, GDANet, and DGCNN, each with 4 instances. While different architectures are used, predictions exhibit high level of correlation. On the other hand, this matrix represents the correlation within an ensemble based on a single architecture, DGCNN, but consisting of 3 sampling strategies: patch, curve, and random, 4 samples per strategy. Diversity is larger when using various sampling strategies compared to combining different architectures. Note that using only random creates a relatively correlated ensemble, underscoring the superiority of employing different sampling strategies. Our code is available in the following link, and we also have a demo that lets you try and examine clouds for Model C. Thanks.